Essentially, Force Platform is a device that allows us to measure predominantly vertical ground reaction forces, but depending on the type of equipment you have, you can also look at some horizontal measures of force. But I guess for the sake of today, keeping it relatively simplistic, we'll talk about kind of measures of vertical ground reaction force.
Hi, Shaun. It's my pleasure to have you on Evidence Strong Show. If you could briefly introduce yourself.
Hi there. So my name's Shaun Joffe, currently a senior lecturer at St Mary's University based in Twickenham in London. My background, broadly speaking, has been in strength and conditioning, but having been a fairly average weightlifter, a lot of my interest and focus was particularly around Olympic weightlifting. After working with the English Institute of Sport for a number of years, I ended up working with the British Weightlifting performance program in preparation for the Rio cycle, which was mainly for the women's team. And that was in kind of a strength and conditioning performance scientist capacity. So anything from supporting some of the weight room-based training to a bit of strength diagnostics, some barbell trajectory analysis, and then anything kind of rehab-y related. So kind of quite a broad and overarching umbrella. Since then, I've been doing a bit more research, doing a PhD in around weightlifting, particularly around some of the physical determinants of weightlifting performance, looking at some of the measures that we collected when working with the team during that time, which I also know that they're still doing now. And then I also coach my own group of weightlifters at Woking Weightlifting Club and some through St Mary's University as well. So for the most part, like over the last few years, I've kind of perhaps funneled myself more and more more specifically towards weightlifting, both from a research and from a coaching perspective.
Awesome. That's amazing for Evidence Strong, because we are interested here in weightlifting, Olympic weightlifting in particular. So very excited to have you. And the topic we have in mind for today is Force platforms. So let's start with the basics. So what is Force Platform and why we should care?
Yeah, so essentially, Force Platform is a device that allows us to measure predominantly vertical ground reaction forces, but depending on the type of equipment you have, you can also look at some horizontal measures of force. But I guess for the sake of today, keeping it relatively simplistic, we'll talk about kind of measures of vertical ground reaction force. So it allows us to be able to perform a range of different tasks on that Force Platform to be able to measure the force output. And from that, other measures can be derived from things like impulse. Therefore, we can calculate velocity, acceleration, displacement, power output, rate of force development, plus a range of other interesting variables that may help us to better understand what's happening during the movement. And if we can collect that data and know that that data is then reliable, then we can track that data over time and see if it is responsive to particular training interventions, and then also which of those particular metrics are associated with the performance that we're interested in. So in the context of weightlifting, we're largely interested in the ability to generate large amounts of vertical ground reaction force, particularly during the pull and the squat phases. And there's a range of different things you can use the Force Platform there, but the technology actually allows us to be able to measure those qualities and then have to look at how they change over time when we undergo weightlifting training.
Awesome. So I think it will be super useful to go through an example so we can actually see what the task is, how the task is set up, what is measured, and how it looks on the side of a researcher, so on your side with the data, and how you then interpret the data to give coaches or yourself, if you are a coach, some additional knowledge to inform your coaching practice, I guess.
Okay, yeah. So I guess what I'll focus specifically on the isometric pulling positions, which is what most of my research has been focused around. You could argue there's many other tests that you might look at. You could look at the force trace within the actual lift itself. You could look at a range of jumping tasks as well. And for the interest of time, perhaps what we'll do is focus specifically on the isometric pulling tasks and have a look at what those actually look like and what types of information that gives us from an analysis perspective, but then also what information and what variables we might want to feed back to coaches. So if you bear with me, I'll share my screen with you quickly. Okay, so this is the system that we use, St Mary's. It's the system I used when I worked with British Weightlifting previously and through the English Institute of Sport. This is the valve force deck system. So we have a customized isometric rig set up in our PEC at St Mary's, which is a great little setup. I can share some images of that, and it allows us to be able to do this kind of testing. And when we had it designed, we had it specifically made so that we're able to measure not just the isometric mid-thigh pull position, but also positions corresponding to different key phases within the lift itself. So I'll get onto this in a bit more detail later on, but it allows us to be able to measure the start position, the start of the transition phase, and then the mid-thigh pull position. So this is some data that I just happened to have collected with myself just yesterday while I was in the gym, just having a bit of a play around on the system. And what this represents is essentially the force trace of the isometric mid-thigh pull test. So what you can see here, hopefully you can see my cursor hovering over the screen.
Yes.
What we have here is essentially what we refer to as a force time curve, and this illustrates essentially me pulling maximally against the bar and expressing as much force as I can, provided that I don't deviate from the key technical model of that position. Now, again, in the interest of time, I'm probably not going to go into all the details around the setup. For those who are interested, there's a great paper by Paul Comfort and some of his colleagues around the actual precise setup. But essentially what this position looks like is that it corresponds to the start of the second pull. So it coincides with approximately when the knee reaches its greatest knee flexion angle and the torso is orientated like vertically. And that's essentially what constitutes like the start of the second pull phase. So broadly speaking, I won't go into any much more detail than that, but hopefully everyone listening has a fairly good idea of what the start of the second pull looks like. So if we have a look here, this is essentially me standing quietly on the force plate. So it's just essentially measuring my body mass. And then what we have here is this very quite rapid, instantaneous rise in force. And that's an important aspect of the test, particularly if we're looking to try and obtain some time-dependent measures. So things like rate of force development or force at particular time epochs, or even impulse. So all of those three options kind of give you they're answering the same question about how quickly you can generate force, but they're just slightly different ways of looking at it, and some have slightly different reliability associated with it. But essentially it allows us to look at how quickly you can generate force, not just the magnitude. So if we cue the test correctly to be done with, the particular terminology is to push as hard and as fast as possible. So even though it's a pulling based movement, the cue is to push and it's to be done as hard and as fast as possible. And that participant should continue pulling until there's a clear plateau or even decline in force, in which case the test would cease. And you can see from the timestamps along the bottom, it doesn't last particularly long. I perhaps probably could have held on to this a little bit longer because it still looks like there may have been a continuous rise here. But if we look across the trials, there's a bit of a plateau after those first few. So I can be reasonably confident that maximal measured there is representative of my maximal abilities. So what we have here are essentially two measures, something that represents this rise in force here, which would be referred to as like your rate of force development. And we can pick out particular time epochs that we want to look at that data within. So something perhaps relatively short, so perhaps something within 0 to 0.5 at 0 to 50 milliseconds, 0 to 100 milliseconds, 0 to 200 milliseconds. Those are typically the time frames that we're quite interested in. For the most part, the reason for that is that those time epochs kind of correspond to those rapid ballistic propulsive phases that we often observe in a range of sports. So ground contacts during sprinting, vertical jumping, changes of direction, Olympic weightlifting, all tend to kind of fall roughly within those time epochs. Weightlifting perhaps will have a little bit more time to generate force in the second pull compared with something like a ground contact and sprinting. So we might look at that time epoch anywhere between 0.1 and 0.2 of a second, so 100 and 200 milliseconds. And essentially by looking at the steepness of this curve will allow us to obtain some data with regards to how quickly someone can generate force. So in addition to that, if we do the test correctly, then we can also obtain this peak measure. So that represents your maximal force producing capability. So it's not just how quickly we can generate force, but also your maximal force generating capabilities. And then from that kind of gives us two measures which are representative of arguably a degree of overlap between them, but arguably representative of the two different neuromuscular qualities. Now, maximal strength, this maximal ability here in being able to generate force, does predict a certain degree of variance within rate of force development. So depending on what type of test you do it within, but I believe it's somewhere between 40 to 50%, maybe a bit higher. Let's say approximately 50% of the variance is predicted based on your maximal strength characteristics. And so there's a degree of that rate of force development that is explained through other things, which I won't go into to the depth. It's certainly not my bag to know it from the deepest neuromuscular perspective. But essentially, there are other mechanisms at play from a neural perspective about what actually allows us to achieve that very fast rate of force development. So essentially, this allows us to be able to obtain data around the strength characteristics relating to the start of the second pull. Now, I'm not going to switch to a different test because the force trace will arguably look exactly the same. But one of the other things that, particularly around my research and something that I'm sure that we'll discuss later on, is we've also tested the start of the transition phase and then the start of the first pull phase. And that was the idea. The idea behind that is to look at if there's a particular strength deficit corresponding to a phase of the lift. So although we might be able to obtain a maximal strength measure in what would constitute the mechanically the strongest position throughout the pull, which would be the mid-thigh pull, we can also look at the maximal force producing capabilities and rate of force development in other phases of the lift. And so what we'd see is if we were to perform those same tests, that the general force trace would look relatively similar. So we'd see, again, something like this, where the participant is standing quietly on the force platform, and then we'd see this quite rapid rise in force and then a peak. So it would look very, very similar, but we'd be able to obtain maximal force measures, but corresponding to different phases of the lift. When you actually use this system and you actually look at, for example, the results table, it generates a hell of a lot of data that you can interpret, and that's just from a single force trace. In fact, you can expand this even further to include even more variables. And obviously, we're not going to go through every one of these now, but it just illustrates the type of analysis that can be done just from that single force trace. Now, it's important that we also consider that not every one of these variables is going to be particularly reliable. Even just at first glance, if we have a look across the 3 trials that I performed, we can see some measures actually have much poorer reliability than others. So these net force at 50 milliseconds, these rate of force development measures, are actually quite poor within the shorter time epochs. But as that time epoch increases, so 150, 200 milliseconds, that reliability actually starts to increase. And that's a pretty consistent finding across the literature, is that those early time epochs have poorer reliability. Now, this is where perhaps one of the contradictions that we face is that, well, perhaps not a contradiction, but a challenge that we face is that those shorter time epochs are the ones that we're most interested in, but the ones that are actually less reliable. So it then begs the question, what do we do? Which ones do we look at? If we look at the ones that we think are important, they actually give us perhaps less reliable data, and the ones that are less relevant give us more reliable data. So it's an ongoing question, and perhaps something that we haven't necessarily entirely solved. I will again draw reference to some of the research that we've done in a meta-analysis around some of this as well, and perhaps some of my interpretations, but at least kind of gives some insight as to some of the data that we might be able to look at. But for argument's sake, what I'm just going to perhaps draw towards is kind of these peak measures, so net peak force and peak vertical force, and then rate of force development, essentially these time-dependent force-time characteristics. So yeah, I mean, that kind of gives us a bit of an oversight of those 3 different positions. So again, the force trace would look relatively similar. We can get a lot of information from them, but for the most part, we're just perhaps largely focused on just the type, how quickly they can generate force within particular time windows or time epochs, and then the maximum amount of force that they can generate within that lift.
All right, so we have rate of force development, then peak, net peak.
So we have net peak force and kind of gross peak force, and both of those measures have been reported in the literature, and depending on where you go, some will look at the net, some will look at the gross. Essentially, the gross is inclusive of body weight. So when you look at the data, if you stand on the force plate, it will obviously, the force output will rise to however much your body mass is, and then you perform the test, and then in addition to that body mass, it will record your force when performing the tests. And some report the data with the participant standing on the plate, and some report it without. So what we've done in the past is report it without. So our rationale behind that is if you stand on the force plate, you get, 1 times body weight's worth of force. It doesn't necessarily make a huge amount of sense to include that in the reporting, because that's just you standing on the force plate. So we've taken that out of the reporting. You could argue there's actually not too much difference. You're kind of getting a measure of the same thing as long as you standardize it. And there was a paper published back in, I think, like 2013 by Beckham, who actually ran correlations of the two. And again, they're pretty close, and obviously, as you'd expect, correlate very highly with one another. And so you could arguably just choose whichever is best and best suits your rationale, as long as you're consistent with what you do. So it doesn't make sense taking both. You would choose one measure because they're arguably representing the same thing, but just presented slightly differently.
Awesome. So that's a technical detail. You just make a decision one and almost can forget about it later as you do the trials and analyze the data. Okay, we run the trial. We have some data. What do we do with it now?
So I guess this is where we're at, is trying to infer what does that data mean. Perhaps we'll get on to looking at what some of the research or what our research has shown so far. But I guess the idea behind it is that, well, let's see how well it correlates with performance. And if it correlates particularly strongly, then we just use some simple regression techniques to be able to say, right, well, if you need to be able to perform a snatch of this load or a clean and jerk of this load or a particular total, what do you need to be able to do in either of these tests to be able to attain that particular performance goal? So in order to do that, firstly, you need to be able to run some correlational studies or some regression type studies, and then from that be able to obtain some data, be able to make that inference. So yeah, I mean, at this point, perhaps worth looking at some of the research that we've done so far. If I can share my screen again, the first study I'm actually going to talk about actually included the counter movement jump, which we haven't necessarily discussed extensively, but I've only included it in the first of the studies that I've looked at so far. So this study was titled Neuromuscular Predictors of Competition Performance in Advanced International Female Lifters, Cross-Sectional and Longitudinal Analysis. So again, just for the sake of making sure everyone's on the same page, a counter movement jump is essentially standing on the force plate, either holding hands across hips. We standardize it as holding a dowel across the shoulders and then performing a maximal vertical jump as high as possible. Obviously, the main obvious metric that you'd obtain from that is the vertical jump height, but if you perform it on a forced platform, I think you could probably get double the amount of variables that you're able to obtain from an isometric test. So again, it gives you a huge amount of data to look at. We largely, for the sake of this study, we looked at the main kind of biomechanical outputs. So force, velocity, power output, and vertical displacement. So there's so many more things you could look at. We kept it relatively straightforward to those few. So for this study, what we looked at was a stepwise multiple regression, and we looked at snatch, clean and jerk, and total, and to see how well those could be predicted from the isometric mid-thigh pull peak force, and then the counter movement jump peak force, peak power, peak velocity, and peak displacement. So not only did we do that, we also looked at like the annual change between two consecutive years. So we averaged the data out for 1 year, and then for the second and for the following year for all of those measures, so the performance measures and the force plate measures, and then looked at whether changes in those force plate measures were associated with changes in the performance measures as well. So the idea behind that is, obviously, when we infer from correlational studies that are purely cross-sectional, then we have a challenge of, not inferring causation from correlation. So it doesn't answer that, it doesn't solve it, but it at least is in the right direction of trying to show some association with change in certain characteristics and changes in performance. So some of the interesting findings. So firstly, these were the two variables that were included in the regression, okay, which is why they're the only ones that were plotted. So as you can see, isometric mid-thigh pull peak force showed very large, if not nearly perfect correlations with snatch, clean and jerk, and total. And you can see that in the R values here. So 0.83, 0.90 and 0.87. And then for the counter movement jump peak power, we can see is this was between 0.88, 0.76 and 0.83. So slightly lower in the clean and jerk, slightly higher for the snatch. Certainly what we'd consider at least very large correlations with performance. We then ran the stepwise regression. So that allows you to enter multiple variables in to be able to predict performance. And what that actually allowed us to obtain was an even stronger prediction. So this is similar to the R, but the R squared value. So that can essentially tells you how much variance in snatch, clean and jerk, and total performance can be predicted from those variables. So in this case, 94.2% of variance in total can be predicted from the isometric mid-thigh pull and the counter movement jump peak power. So that's, again, very, very strong. You'd very rarely see this level of prediction from two test variables in any sports science literature. So it tells us that the output in maximal strength and ballistic jumping power output is are very strong predictors of performance. So that immediately gives us some inference into how we could evaluate the qualities within these lifters, and then also to evaluate, right, where are they in relation to our standards? Do they fall short? And the way in which you could structure this formula is enter in, let's say you have a nice working Excel spreadsheet. I want to target a 220 total. Okay, plug that in. That will tell us that how much of an isometric mid-thigh pull they would require, and then how much of a counter movement jump peak power they would require in order to be able to obtain that total, with some degree of estimation of what the error of that might be either side. So it would give us some fairly accurate prediction. Now, it's important to acknowledge that this is done in a particular cohort, and the limitation of these types of studies is the model reflects those who are included in it, and you can arguably try and apply it to those who weren't part of that population, but there are some errors that come with that. So it's a relatively small sample, but it's one of the limitations in this type of research that we just have to accept and take the findings with a pinch of salt. But the next part of the study is to look at which of these variables actually associate with any change over time. So firstly, which of them actually showed any performance improvement and which of those didn't. And we can see the snatch, clean and jerk and total weren't statistically significant between the 2 consecutive years. And that's because the nature of weightlifting, some people make progress, some people plateau, some people actually show a bit of a decrement in their performance over that time. But actually for the question we're trying to answer was actually quite helpful, because then we've got data of people who didn't make progress, people who showed a decrement in progress, and some people who showed an improvement in their progress. So the next thing really was looking at the stepwise regression with the delta values, so a change in performance. And what we can see here is, well, firstly, the model actually excluded all the jump variables. So what it only included was changes in maximal isometric force, but eliminated all of the counter movement jump variables. So this was the next level of the study. What we looked at was the delta values, or the percentage change across 2 consecutive years, and how changes in the force plate measures associated with changes in performance. So in the stepwise multiple regression model, it actually excluded all of the jump variables from the model, so suggesting that it only included a measure of maximal strength that was associated with the change in performance over time. So that's why I plotted each of these, again, just on a simple scatter plot showing changes in snatch, clean and jerk, and total performance with changes in isometric mid-thigh pull peak force. And we can see is at a fairly large correlation between 0.64 and 0.65 in terms of the change in isometric mid-thigh pull peak force and snatch, clean and jerk, and total performance. And I think that's what's really interesting from my perspective, is that although the counter movement jump peak power output was strongly associated with weightlifting performance cross-sectionally, it's actually excluded from the model when you look at it longitudinally. And only the measure of maximal isometric force was retained in the model to predict performance improvement long term. So
I have to ask why.
So I've tried to conceptualize this on a following slide, and it's not perfect. Oh, sorry. Here are the regression equations for the total snatch and clean and jerk as well. And again, you can see between 41 to 42.5% of the variance is predicted from these two. So slightly less of the variance is predicted from improvements in maximal isometric strength, but it still explains a fairly substantial portion of performance improvement over time. So my thoughts on this is, from a relatively simplistic perspective, we think about this in terms of the force velocity power curve, and we see where isometric mid-thigh pull peak force and counter movement jump peak power occur along that kind of force velocity continuum. What we have is kind of a change predominantly up at this region of the curve. And if you actually look back through, I'll go back to that previous slide, what we saw was actually the peak force in the counter movement jump was statistically significant across the 2 years. So there was a change in counter movement jump peak force, but it wasn't associated with change over time. So that might suggest that there's a larger change in isometric peak force up here, and where counter movement jump is much further along that force velocity continuum. There's a small improvement, but ultimately no change in power output. So theoretically, what that might suggest, and again, it's only theoretical, we didn't test it directly, is that there's more of a leftward shift in power output towards the isometric region of that force velocity curve. And that kind of makes sense, because if you think about where most weightlifting training occurs along this curve, it's probably somewhere closer towards the isometric region of the curve rather than towards the high velocity end of the curve. So it's kind of a illustration of the specificity of training. If you train with heavy loads to improve maximal strength and the ability to lift heavy loads, that's going to elicit adaptations that are reflected within adaptations at region of the force velocity curve. So it makes the most sense to me. I'm not sure if that's the perfect explanation or if it explains everything, but I think for the most part it gives a bit of insight as to where, from a neuromuscular perspective, those adaptations are taking place. So I'll move on to the next study, which we looked at maximal isometric force in the start position and the isometric mid-thigh pull, and compared their correlations with weightlifting performance. We already knew that the isometric mid-thigh pull had a very strong correlation with performance, and actually was associated with changes in performance over time, explaining between about 41% of the variance over over the course of 2 consecutive training years. For this, we used both male and female weightlifters, including national and international level. And what we looked at here was simply correlating the variables and then running a statistical test to compare if one correlation was actually greater than the other. And we did that for both absolute and allometrically scaled. And for simplicity purposes, just allometrically scaled is something similar to like a Sinclair. It tries to normalize the performance to body mass, knowing that there's a nonlinear relationship between strength and body mass. So any correlations that might be skewed potentially due to just having a bigger body mass and therefore having a higher strength level, we can slightly control for that by looking at the data allometrically scaled to body mass. So we've got 2 isometric pull positions. So the isometric start position pull and the isometric mid-thigh pull. And as you can see, the isometric start position pull is performed at essentially where the bar would be when loaded from the floor. So the bar would be approximately would be 22.5 centimeters, or the center of the bar, 22.5 centimeters from the floor. So as you would start. So because the isometric mid-thigh pull was done with a clean grip, we kept the clean grip, even though we looked at both the snatch and the clean, just to be able to make comparisons between the 2 positions. Now, firstly, what we did is just compare, is there a statistically significant difference between the force production in each of the positions? Intuitively, it makes sense that there would be, but it's nice to be able to put some figures to it. And we can see that in both cases, when we look at the data in absolute and allometrically scaled terms, there is a statistically significant difference between the 2, with the isometric mid-thigh pull showing substantially greater force production. So we know that we can produce much more force at that second pull than we can in the start position. I haven't presented the data here, but the ratio was somewhere around 55 to 60%. So we can produce a pretty substantially larger amount of force in that isometric mid-thigh pull position than we can in the start. So the next part of it was to actually run some correlations, and we can see here there's quite a lot of information on these figures. But what you can see is that, and let's particularly paying attention to the left-hand panel, is that those are all the absolute measures. And when we look at the snatch in relation to the two isometric tests, the isometric mid-thigh pull still shows similar correlations to the previous study. So 0.83, 0.88, 0.86 for snatch, clean and jerk and total. But interestingly, the isometric start position pull actually correlates even stronger. So it actually has a larger correlation, or at first sight looks like it has a larger correlation. So 0.94, 0.95, 0.95. And then when you allometrically scale that data, the correlation magnitude actually decreases slightly. So you can see, for example, in the snatch, the correlation is 0.83. When you then account for body mass, it reduces to about 0.51. So that's predominantly, or most likely, is just a product of just having included body mass in the correlation, or not accounting for it, gives you a stronger correlation. So this just allows us to control for that slightly. So the correlations get slightly weaker, but the same trend seems to be quite apparent. So if we compare the 2, it seems as though in the snatch 0.51 versus 0.83, clean and jerk 0.65 versus 0.85, and then for total 0.59 versus 0.85. Now at first sight, it looks there's a difference there, but we actually have to compare that statistically to say that there is a greater correlation or not. And we use what's referred to as like a Fisher-Z conversion. And then you can run like the equivalent of what's a t-test to be able to test if there's a difference. And interestingly enough, again, there's quite a lot of data here, but I'll direct you to the bits I want to highlight. So in terms of the snatch with a combined male and female group, there was a statistically significant difference in the absolute data, and same for total. So in that case, the isometric start position actually showed a greater correlation with performance than in the isometric mid-thigh pull. And then in the allometrically scaled data, it was only for the snatch lift. So when we looked at the other data, like without kind of breaking rules of best practice in research, like it was those numbers were like approaching statistical significance. So some of them were like 0.056 or something like that. So we can't say that there is a statistically significant difference. But with your coach's hat on and knowing that we've got a relatively small sample size, perhaps a few more participants would have actually given us enough power to actually observe that significant difference. But at the very least, when we don't allometrically scale that data, in total, the isometric start position pull actually correlates better than the isometric mid-thigh pull. And that's me quite an important and really interesting finding. And you could speculate what the rationale or the reason for that is. And I've perhaps landed on a few. Firstly, if we look back to first set of data that I analyzed, was just comparing the two positions. That start position is just the weakest position of the lift. And that intuitively just seems logical that the weakest position should be the limiting factor to how much load you can lift through a range of motion. When you see that in a back squat, you see that in a deadlift, see that in a bench press. So when people have done those studies and run similar comparisons between correlations, that same trend seems to be apparent. And so not only is it present in strength-based exercises, but also in these kind of what we refer to as like quasi-ballistic quasi-strength. So something it's a ballistic task, but you're intending to lift the maximal load. So it's not quite strength, it's not quite ballistic, it's somewhere in between the two. But the same pattern seems to be apparent that the weakest position seems to be the best predictor of, or best correlate to performance. So if we look at the mechanics of the actual lift itself, at the start of the lift, we have a bar that's relatively still with the exception of some like dynamic movement. But we have to overcome the inertia of the bar. The bar's going to move relatively slowly off the floor, and we're already in a mechanically weaker position due to muscle lengths and also just mechanical advantage or even disadvantage. So you could argue, if you think about where that position functions across that force velocity curve, and again, it's probably somewhere closer to the isometric part of that force velocity curve. But as we progress through the movement and we get close to the start of the second pull, the bar's moving somewhere close to, somewhere 2 meters per second. The center of mass of the lifter, or the combined center of mass, or the combined or the system mass, is moving probably somewhere close to the speed of the actual bar during the pull phase. In which case, that phase arguably is functioning across a different portion of the force velocity curve because it's moving at much higher velocity. So the specificity of the start position pull to the start position is arguably greater than the isometric mid-thigh pull is to the start of the second pull, just because the velocity at which the start of those phases differ. So that may partly explain why, but then that would lead to the next question: do we need a more specific test than an isometric test to be able to evaluate the isometric, also to evaluate the start of the second pull? And then it just opens up lots of questions, and you're like, where do you go next? And you have to reel yourself back to some basic questions that you have to answer, because it's very easy to get carried away with all the other questions that come about from these speculations and trying to interpret these findings. Okay, so this was the kind of the third study that I'd done, and this came roughly around the same time as COVID, because we intended to do a new study, a more prospective study, and we had some ideas based on those first two, but unfortunately COVID got in the way, so we then had to perhaps look at what else we could do to try and continue answering these questions that were evolving. And so what we looked at was quite nicely summarized in the title, which is the relationship of lower body multi-joint isometric and dynamic neuromuscular assessment variables with snatch and clean and jerk performance in competitive weightlifters. So that was all different types of force plate measures. We included some studies that also did it on some perhaps fairly older technology, so used things like contact mats so they could calculate jump height from those variables, and then use methods to predict power output rather than measuring it directly on a force plate. But then we also included dynamic measures like back squat and front squat 1 rep maxes. And so I'll go through the process relatively quickly. Obviously, in order to do a meta-analysis, you do a systematic search through some databases that pulls out any articles that look relatively similar to what you want to investigate. And from that, we were able to obtain 12 studies that we included in the analysis. And from that included 395 participants, 12 returned from those 12 returned studies. And from that, we had 15 variables from 5 different assessments. So there's 5 assessments. The reason why there's 15 variables is that there's obviously in an isometric test, you get multiple variables. From a counter movement jump, you get multiple variables. So we had an opportunity to look at quite a different range of neuromuscular assessment variables in relation to performance. Now, I'm not going to go into every single one of these. I'll kind of consolidate this on a tidier slide following. But this kind of goes to show just the 15 different assessments. And this was for just the snatch. And then we also did it for the clean and jerk. So we actually had 30 separate meta-analyses in one. But we consolidated it into this tidy figure here and rank ordered them based on their correlation magnitude, from the right-hand side being nearly perfect positive correlations to some that actually showed a little bit of negative at the far end of the 95% confidence intervals. And you can see here quite nicely where each of these different neuromuscular assessments and their particular variables fall in relation to one another in terms of correlation magnitude. So just for a bit of kind of insight, the vertical dotted lines represent like descriptors that we use in research to be able to almost descriptively quantify the correlation. So rather than just reporting the R value, we can say, right, is it trivial, small, large, very large, nearly perfect? And that just allows us to descriptively describe the correlation. And so what we can see, the first here is plotted for the snatch lift. And what we can see, first of all, the strongest correlations with snatch performance is front squat and back squat with a correlation of 0.93, 0.94. Then we have squat jump and counter movement jump peak power, which is, again, very interesting, very strong correlations. But the first study actually showed that that variable didn't track particularly well with long-term performance improvement. And then we get to the isometric mid-thigh pull peak force. I will add at this point that at the time that we did this meta-analysis, there'd been no other studies that had looked at the start position or the transition position. What's actually been done since is several other studies and actually confirmed our findings. So we showed that the isometric start position pull significantly correlated with performance better than the mid-thigh pull, and that's been substantiated since with another study. In fact, two other studies, one by Ben Ziv and another by Kyle, I'm not sure if I might butcher his surname, Kyle Rochow, something like that. So again, really interesting to show that these findings have been validated again since then. One of the other kind of interesting points is that if you actually look at the isometric mid-thigh pull values, what we have is the isometric mid-thigh pull peak force shows the greatest prediction. And then next we have force at 250 milliseconds. And then as we move further down the figure, we see that the time epochs reduce. So 250, 200, and then 100 milliseconds. And then where rate of force development has been calculated by force divided by time, then we can see again the same trend emerges. So rate of force development between 0 to 200 and then 0 to 100. So there's two possible interpretations for that. Firstly, the shorter time epochs are less relevant and have lower correlation with performance. However, if you also look at the confidence intervals of these, this suggests that that data is then arguably less and less reliable, even though we haven't necessarily reported the reliability here per se. The big or the very large 95% confidence intervals means that data, if you test it again, could fall anywhere within that with 95% confidence. So that just suggests that there's two potential explanations for that. It doesn't correlate, or they correlate less with performance, and that they are the less reliable measures to look at. So they might still actually be highly correlated or be best associated with performance if you can get the reliability for them. But so far, from all the studies that we included, they actually show the lowest correlation and have the largest 95% confidence intervals as well. But if we were perhaps to allow ourselves to speculate that potentially the less time constraint force producing characteristics are more important to performance, then that suggests how much the magnitude of force you can generate rather than how quickly you can generate is more important for weightlifting performance, which perhaps goes against the grain slightly because we often think of weightlifting as kind of an explosive task, and it is. But we often, in describing weightlifting being an explosive task, we focus on the second pull. But if you actually think about the time available to generate force in weightlifting, we have really from the start of the first pull until the end of the second pull, which in some case can be a second. And that arguably is actually a lot of time to generate force. And you can generate a hell of a lot of force in those movements, and therefore potentially less limited by rate of force development and potentially more limited by just the ability to produce force in higher velocity movements, if that makes sense. So potentially, just force out particular velocities. And so my interpretation of this is that most of this points towards maximal strength being the important and most important predictor of performance for weightlifting, which is probably no unique finding and nothing too surprising. But I think perhaps at least from my perspective now, from a coach rather than a researcher, is I then just look at maximal strength being the ceiling to what, or the ultimate limiting factor to how much load you can lift in the snatch or the clean and jerk. So rather than thinking about these as different qualities that they all require certain amounts of attention at the same time, I now start to look at this from the perspective, right, well, unless I've raised your maximal force capacity, whether I evaluate it in a maximal or in a front squat 1RM or a back squat 1RM or a mid-thigh pull, we need to raise your maximal capacity first, and then we can potentially utilize that ceiling or that buffer of strength that we have available and start to translate that into the technical side. So unless you raise that ceiling in maximal force producing capabilities, you can improve technique all day long. If you don't improve the capacity to be able to generate more force, then you're ultimately going to be limited. So I then start to think about what that looks like in the context of maybe like periodization and how this falls within like perhaps longer term planning. And I use a lot of this data now in setting out my expectations around, right, well, I need to achieve this target in our maximal strength measures, be they isometric pulls or back squat, front squat, 1 rep maxes, a certain amount of time before we go into competition. And then if I know that I've attained those targets, then I can perhaps target my training focus towards more technical development. And then I know I've raised their capacity and that they have the potential to be able to achieve that total. Then it becomes a case of, right, well, then we push more from a technical, translate that into technical application. Doesn't mean I don't still do technical work where we're trying to raise strength capacities, but it's allowed me to organize my thoughts better in terms of how I organize let's say a 3-month lead into a competition, for example. Okay, so this is just been working on recently, and this is including the transition position of the isometric pull series. And we didn't include this in the first study for a few reasons. Firstly, the main question that we had at the start was, is there differences between the strongest and the weakest position of the lift? So at that point, including the transition phase didn't necessarily make sense. We just wanted to identify where was the strongest and the weakest positions. And then within those, did either of those better correlate with performance? The idea of including the transition phase is that if you think about it from the force time curve perspective of the lift, and for those, just for the sake of visualizing, if you look at Shaun Joffe's paper on the applied analysis of weightlifting, the weightlifting technical model, there's a really nice figure at the back there that shows the force time curve of the lift. And what you can see during the transition phase is what was referred to as an unweighting. So the force output actually drops below the system mass. And sometimes that's been speculated to be a strength deficit reason. It's also being speculated to be just a technical reason. It might be a combination of the two. It might be influenced by anthropometry. Again, these are some of the questions that we have. But if you look at it from just a strength capacity perspective, what is typical across a fairly large proportion of lifters. Again, in this study, we used 31 of the British national and international level lifters. And what you can see is that there are significant differences between the isometric start position pull and the transition, and then between the transition and the mid-thigh. So there are significant differences between each of those different positions when you look at them in relation just male, female, and also as a combined group. So what that affirms is that we do observe this ascending strength curve characteristic. So we get stronger the further and further you move through the concentric phase of the pull. Now that's interesting for a few reasons. One, again, it just illustrates that particular transition position, that there isn't necessarily a deficit in force that we observe in the actual force time curve, so that there might be something else that explains that, but at least then gives us also some relatively normative data about where people should be at each of these different positions. So if we now have some relatively consistent data that allows us to be able to say, right, but in each of these positions, this is where what a normative standard would be for your level or for a particular total. If you're looking for a particular total, this is what you should be theoretically be able to achieve. That allows us then to be able to be a bit more prescriptive with this data in order to be able to inform training programs. These are some of the conclusions that I think I've made so far that I think are quite relevant for practitioners. So firstly is that the isometric mid-thigh pull peak force shows very large correlation with performance and is associated with performance improvement over time. So what we can conclude from that is that maximal strength is something that determines performance improvement. That shouldn't be a shock to anyone, but it's something that's nice to have some data that partly verifies that, we need to actually prioritize maximum strength development within our program. But again, hopefully that's no news to anyone who's watching. The isometric mid-thigh pull time-dependent measures, so force at or rate of force development, actually indicate that increase in correlation magnitude or strength with longer time epochs until no time constraint. So the shorter time epochs have greater variation or variability and also poorer correlations with performance. And as you increase the amount of time that you have available to generate force until you have no constraint on time, so just a peak force measure, the correlation magnitude seems to increase continuously. So that suggests, or certainly partly indicates, that maximal strength is the important measure, but we have to accept that we have poorer reliability in some of those time-dependent force time measures. The isometric pull from start position or the isometric start position pull peak force also shows nearly perfect correlations with performance and is significantly greater than the isometric mid-thigh pull. And that's also been substantiated with some further studies that have been done elsewhere since then. So it's nice to see that has been some supporting data to show the same thing. Again, that kind of leads to potentially that position being a better test to be able to evaluate maximal strength and use of a surrogate measure to infer weightlifting performance, as opposed to the isometric mid-thigh pull. There's no significant correlation between the isometric mid-thigh pull and isometric pull from start position when allometrically scaled to body mass. And this wasn't actually a conclusion that I discussed when we were on that study, but interestingly, when you allometrically scale the data and then correlate those two measures, the start position and the mid-thigh, they're actually very poorly correlated with one another. And again, I can only speculate as to what the reason for that might be. One of them might just be that they are to some extent independent qualities, and that they might then be, potentially trained not necessarily in isolation, but more targeted focus towards either of those might actually lead to more position-specific changes within either of those positions. But that's purely speculation, and I'm still kind of trying to get my head around why they actually might not necessarily be particularly well correlated with one another when you control for body mass. But it's certainly an interesting finding. The back squat and front squat 1 rep max continue to be some of the best predictors of performance. And from a practical perspective, for those who don't have force plates, they're probably the easiest and most available ways in which you can measure maximal strength. And I suspect that the vast majority of people who coach weightlifting will have some way of quantifying maximal strength in a back squat and front squat, be it a 1RM or a 3RM or something of the sort. But those are still probably the strongest and then most available ways in which we can evaluate maximal strength. And arguably, I think everyone probably should be doing some kind of back squat or front squat 1 rep max test, unless they have a valid reason to not. But considering how well correlated they are with performance and how available they are, it makes sense that they are a pretty staple part of monitoring and testing practices within weightlifting. And then lastly, counter movement jump and squat jump peak power output show also nearly perfect correlations with performance. But of the one and understandably relatively limited sample that we've conducted longitudinal analysis on, actually show that metric doesn't necessarily associate with change in performance over time. So it might be a good cross-sectional reference of just evaluating someone's power ability. So perhaps lends itself well to like talent identification or something like that, but might not necessarily be something that translates to performance improvement over time. So again, it's not a case of throw the baby out with the bathwater. There's potentially still some great and real interesting data that may come out of counter movement jump testing, but from the data that we've looked at so far, it suggests that it's not something that shows associations with performance over time. The one thing I would say is that the variables included there were relatively limited, and I think since then there's also been some nice information published by Shaun Joffe looking at the more phase-specific changes or phase-specific impulse characteristics, and not only are they strongly correlated with performance, but have really, really good reliability, and so arguably they're going to be really susceptible to change if there is any. And I think he's presented some really nice information around some of the case study based studies that he's looked at where it seems to be a sensitive measure to performance. So anything that we've looked at that perhaps suggests that something is better than something else, I never take a wholesale approach of, right, we get rid of that test. I still think there's a lot of value in jump testing. I still think there's a lot of value in the isometric mid-thigh pull. And we've done nowhere near enough information to really confirm that any one of these measures is better than the other. All it's done so far is just sort of point us in the right direction, and also probably lead us to many, many more questions. But I think it at least gives us a nice place to kind of direct our focus for the next few studies. But those kind of are so far my practical applications and interpretations of that data so far. So
thank you so much, Shaun. I think we will stop here, and I will just invite you the second time.
Yeah, I'd be more than happy to come back again.
Awesome. Thank you so much for today.
Brilliant. Thank you very much for having me. And again, thank you for doing this as well. It's great to have some people putting this information out and, sharing this information, because it's there's relatively few platforms that are doing this. And it's been really good. And I've been following it for a few months now. So we've really enjoyed it. So yeah, please keep doing the same.
Thank you.